Recently, I built a quantum support vector machine to predict early heart diseases to streamline the status quo of nearly 17.1 million deaths each year due to cardiovascular diseases. And while I was doing so, I had nothing to base my knowledge off of other than 2+ hour long lectures and 20-page plus research papers. And as much as I love the details in those, the way that I work best when first learning something extremely complex is watching a quick summary or a very simplified version of a video or an article related to it, so I get a basis of understanding of what I'm trying to learn. But this time, I didn't have access to that. I couldn't really find anything on the internet. So I thought, why not create one? Let's get into it. So, quantum support vector machines are a quantum machine learning algorithm that use the principle of quantum mechanics to perform classification and regression tasks. And in this case, we're more interested in looking at regression, since that's what's used for prediction purposes. But classification is also involved as the computer tries to learn the differences between the data we're observing. In this case, let's simplify our data down to apples and pears. And after a certain point, I'm trying to predict what will happen next. If I had a massive bucket of apples and pears, I know that I would be able to sort them out. But if I didn't know what any of these fruits were, it would be a little bit harder. And that's the position that our quantum computer is in. Our first step is to prepare that data in a manner that is understandable by the quantum computer, because currently we're working with classical data. So we'll do this through a quantum feature map that maps classical inputs onto its corresponding equivalent quantum state. There's multiple feature map circuits that we can use, such as the quantum Fourier transform or amplitude encoding, but both have the end goal to translate that classical input data into a quantum state. Once our quantum computer can read our data points in a vector form, we calculate a matrix, which is an array of numbers that describes how similar each pair of input data points are in their quantum feature representation. And this is done through a quantum kernel calculation. The results from this matrix can help us classify apples or pears. How it works is that a mathematical operation with the vectors of the quantum states are calculated to obtain a measure of similarity between those two data points in their quantum feature representation. And that similarity value can help us form a hyperplane so that we can correctly categorize our data into its binary classifications. A hyperplane can be thought of as a line that separates two classes, as it's determined by finding the best possible line that maximizes the distance between two classes so that classification results are accurate. Like, if I were to lay out my apples and my pears on my bed right over there, I would probably keep them as far as possible so I don't accidentally mix up my results or alter them in any way. And once we have our hyperplane through the quantum kernel calculation, then it's our quantum computer's time to do its learning. The goal within this step is to optimize the parameters of our circuit to achieve the best classification results. So it's a bunch of iterations for our quantum computers to learn. Usually, this is the most time-consuming aspect of the algorithm, but it's also vital for the circuit to familiarize itself with all of the data points in order to confidently make the correct analysis. But once our groups of training data are separated, our machine is finally a pro. And the hyperplane's regression can help us make further predictions about incoming test data we haven't worked with so that we can make accurate and efficient predictions. But in order for us to get the quantum computer's results, we have to reverse that initial change that we made before. So this time we'll be mapping the existing quantum states onto its corresponding classical states. So now we have the data that we can interpret easily. Overall, quantum support vector machines have the potential to offer an exponential speedup in comparison to classical support vector machines as they leverage quantum computers. And the ability of quantum computers to perform certain computations in parallel can provide users with a quantum advantage that can improve the efficiency of the existing solution. If you want to learn more about quantum support vector machines in detail, I would recommend that you check out my article below where I talk about how we can leverage them to predict early heart diseases. Basically the project that I was working on before. And if you learned anything new today, I would love for you to comment below. Tell me, what did you learn? If you want to chat anytime soon, my platforms will be in the description box below as well. So I'd love to hear more from you and jam out about anything that you want to. Thank you so much for watching, and I'll see you in the next one. Bye!